Good morning, everyone. Welcome to the Bureau Seminar Series. It's my pleasure to introduce our today's speaker, Mr. Charles Nye, who's talking about rare earth element concentrations in produced water. Let me give you a brief introduction about Mr. Nye. Mr. Nye has served as a research scientist at the University of Wyoming Center for Economic Geology Research, or CEGR, for 5 years. He has been PI for grants studying recovery of rare earth elements, or REEs, from Wyoming's oil and gas co-produced waters. Also, he has been task lead on grants to study carbon capture and storage. Before coming to CEGR, his past scientific work included aqueous geochemistry challenges such as uranium systems and transport of aqueous REEs. He has experience in geochemistry, computer science, project management, and socio-technical systems. He has collaborated with engineers and national laboratory scientists to study the role of microbes in the deep subsurface, treat waste streams from beer breweries and well fields, enhance energy efficiency, and measure REEs in natural systems. His current work includes leading MVA baselining at Wyoming's Carbon Safe Phase 3 site near Gilead and supporting CEGR critical materials extraction efforts led by his colleague Dr. Fleet. So, Charles, welcome to our Friday seminar, and let me turn it over to you to start your talk.
So I'll also try to provide some information on what this data that we collected meant, what it means. So we were motivated when the Department of Energy approached us to study something about geothermal waters and something about rare earth elements and possible recovery of rare earth elements from geothermal waters that would allow a geothermal power station to operate more efficiently without salt problems. Oh, and yes, please do throw questions into the chat box. I'm happy to answer those during. I don't want to cut anything off at the end. So the motivation, rare earth elements are very popular right now because they enable better renewable energy and high tech. So here you've got a battery bank and also a collection of different lasers, cell phones. In order to get a map on a cell phone, you have to have rare earth elements because the best magnets, the best compasses, digital compasses that can be made, use rare earth elements to get as light and accurate as possible. After the Mountain Pass mine in California closed, there were really no domestic sources of rare earth elements. And so it was a place that caused anxiety for a lot of politicians, a lot of people in the Department of Defense, et cetera. Now there are starting to be some places, whether they're fully going to be successful remains to be seen, but we've got a few domestic sources now. The other thing that we were thinking about when the Department of Energy approached us was the domestic challenge of managing produced water. And this is the salty water that's really not drinkable initially, that comes up with oil and gas when you produce oil and gas from the ground. And something has to be done with that brine water. It has to be desalted and purified so that the water component can be used, and then the super salty water has to go somewhere. So we were thinking, why not try to combine problems and get a solution? Yeah. And so what we came up with was, we looked at our resources. We saw that University of Wyoming had the ability to contact various groups in industry and get permission to sample and to take water from their fields. We saw that some of our friends over at the Idaho National Laboratories, especially Hari Nepitpane, would be able to measure the rare earth elements in these fluid samples. And we saw that some of our friends over at the USGS had a statistical screening tool that would allow us to expand a few collection areas to cover all of the United States. So we thought, well, let's put these three things together and get out in the field and do something. So we got all excited. We got everything ready to go out in the field, and we got to see a scene that looks like Texas. This is what an awful lot of central Wyoming looks like. Frighteningly blue sky and desert down below. But this is one of the areas we were able to sample. They have a lot of wells And these wells feed together into gather stations in Wyoming. So these oil and gas wells have to pull up a mixed fluid of oil, gas, condensate, and also water. And it has to go somewhere and be separated out into those phases. And so it goes into one of these gather station tanks, these huge tanks. And it's most efficient to separate them after they've been combined from many wells. So you might have 10, 20, 50 wells feeding into a single gather station. And then after feeding into the gather station and separating out the oil and the water and the gas component, you then can sell the individual components properly and treat the rest. One of the things that some wells had, if they didn't feed a gather station, and at every gather station there was an analogous setup to this, was an oil gas water separator. And this is a smaller tank. It's horizontal, just lets it separate by density into the different phases. And we were able to go up and take a sample off the separator at all times. Every site, with the exception of one, they'll mention when I get to it, let us pull water off the oil gas separator. And this water was surprisingly hot still. The water that comes right off the well is, of course, very hot when you have a very deep well due to the geothermal gradient. And here you can see we're taking the precaution of using a brown glass bottle instead of our usual plastic. The person collecting the sample here, Savannah, is being extremely brave because some of these samples come out around 65 degrees Celsius, which is uncomfortable to hold. But we got all of our samples collected. We came back to the lab. We filtered them. There's tremendous variability when people talk about oil, gas, and brine water. They really are about as closely related as zebras and horses. We've got some that had this rust color particulate matter that was still floating in the sample. But when you filter it, it becomes nice and clear. We had others that had this heavy oil tar-like oil that you had to put a pre-filter, a coffee filter on. We're nothing if not realistic. And after that, of course, you then get the nice, clean-looking salty water, which remains clean when you filter it. And after filtering these, after preparing them, separating them into various components, some that would go for isotopic analysis, some that would go for bulk geochemical analysis, the traditional geochemical analysis we do, and also to a separate aliquot that was sent to Idaho National Laboratories. These all went out to our different project partners to have the different analyses performed. Some of them were done internally by us. And over at INL is where I want to talk about, because Idaho National Laboratories did the analysis that was really cutting edge. This was top of the line 4 years ago. And to my knowledge, I think it remains pretty dang close to the top, if not the top still, 4 years later. They had to go so far as building a clean room within a clean room, which is this plastic enclosure structure. And so Hari, bless his heart, he went into this thing every day and did some of the most exacting column chemistry I have ever heard of. To give you an idea of what it was like, he had two different processes, one for high salt brine and one for low salt brine, using different resins, going through a variety of different extraction procedures. Each one of these boxes is the simplification of what he really did. There are sub-steps on sub-steps underneath each of these. So the guy deserves massive kudos for having done that. But he did it and got the analysis sent off for ICP-MS, and we got the data back. And of course, what do you do first when you get a spreadsheet of data back is just numbers? Well, you throw it all into a chart and you plot it up. And we got a royal mess. It was useful. We could see some things in this chart. This is a plot of log concentration of rare earth elements. This is in nanograms per liter. That's parts per trillion. So it's very, very low concentrations, but measurable. And we can see that it stretches over 3 orders of magnitude. That's one of the things we can get out of this royal mess of a chart. We can also see that there's structure in it. We can see this zigzag structure here. And if you squint and tilt your head a little bit, you can convince yourself that there's probably going to be some samples that have more heavy rare earth elements These are lutetium over here and lanthanum over here. So it's light rare earth elements, middles, and then heavy rare earth elements over here. If you squint, you can convince yourself that probably there's some heavy rare earth enrichment, that it maybe slopes up here. But there's a lot of complicated structure over here. It's distracting, and humans wouldn't want to look at this. Well, not being daunted, we sent the raw data off to USGS, and because they're using a computer model to apply a statistical test to this thing, they were happy as can be. Computers love chewing through nasty, complicated data. But for us humans, this sawtooth pattern is distracting. There's way too many lines here. We can't really work with this. And so we need to do something. We need to normalize it. We need to break it out into some groups. We need to do all those things. So I'm going to step back now, and I'm going to think about how and why we normalize. And then afterwards show you the data, the results, and some future work that I think we need to do, or that we'd like to do. So about normalization. Rare earth elements are basically the F block of the periodic table. There are 14 of them. They go from lanthanum, which is the lightest by mass, to lutetium, which is the heaviest by mass. Some people, when they say rare earth elements, include yttrium and scandium, and it's just up to them whether they include those or not. Sometimes they call it REY when they call it refer to yttrium and scandium. These rare earth elements are all remarkable because they have similar chemical behavior. They all move in the same way. They go the same places. And so when one physical process moves one of these, it will move all of them. When a chemical process moves one of them, it probably is going to move all of them. There's a little bit of nuance. Some minerals will accept the light rare earths, some will accept the heavy rare earths. And it's generally a smooth movement between them in hard rock. That is similar chemical behavior has been established in rocks, and it has also been established in the oceans. But we wanted to know, does it also hold in groundwater, in basement groundwaters, and in oil and gas reservoir groundwaters? So that's something we will discover. These elements, as I said earlier, are important because they are key to many difficult to substitute applications. If you want to build a cruise missile for the Department of Defense, you need a magnetic compass. You need a digital compass that a computer can read to guide the missile wherever it's supposed to go. If you're going to build a wind turbine for peaceful purposes, you need to have a really strong magnet to hold the bearing. And so these rare earth elements have properties that make them ideal for those applications. You can make the smallest, lightest, most accurate digital compass. You can make the smallest, they're still not that small, strongest magnet with these things. And they're not really impossible to substitute for. I mean, if rare earth elements disappeared from the face of the earth tomorrow, you would still be able to do all these things. Your wind turbines would be heavier, less efficient, bigger. Your cruise missiles would be bigger, heavier. There'd be less space for stuff that goes boom in them. But you could get along just fine. The problem is that we want to optimize. We want to get that extra performance. And so we want these rare earth elements. Before I go into the details of normalization, I'll quick answer this question I see popped up. How do you prevent CO2 degassing from the sampled waters and the resulting changes in formation composition before analysis? Would this affect rare earth elements concentrations? Good question, yeah. So the simple answer is we don't. When you pull water up from deep underground, it has to degas. There's not really any way around that. The CO2 that was present at pressure in solution, just like when you open a bottle of pop, it's gonna come out. The question is, can you reverse it? Can you model the reverse and send the water mathematically back down the wellbore, back to high pressure? And you can. We use geochemists' workbench for that. And that's the closest we get to that. Because rare earth elements don't mobilize very well, they don't go into air-based components, they're lost. We don't anticipate that the rare earth elements would be affected by that. There's limited geochemical data on rare earth elements. and their behavior in aqueous systems. So if you wanted me to prove it, I can't. But we can generally say back of the envelope, it won't be doing anything that loses rare earth elements to a gaseous phase. The change in pH that accompanies outgassing could perhaps cause rare earth elements to precipitate somewhere. So it's a fair question. In this talk, we basically assume that rare earth elements are not affected by that. Geochemistry certainly is, and we're able to reverse that. But I don't think I present bulk geochemistry in this talk. Good question. So we have to go back to normalization of these rare earth elements. And as I said earlier, this sawtooth pattern distracts. This is a whole bunch of authors weighing in on what they think chondrites, which are asteroids that approximate the composition of the solar system and thereby what we think Earth's bulk rare earth element content is. They're all weighing in on what they think chondrite meteorites have in them. And it makes the sawtooth pattern. There's huge amounts of variability here, but it's hard for humans to pick out because there's a sawtooth pattern in the way that distracts us. The human eye can't get through that. This particular chart also includes yttrium, like I said earlier, which sometimes is not included, and promethium, which is never included because it's a radioactive element that there's basically none of on Earth. So those two have to be removed. And then you get this pattern, sort of a missing sawtooth pattern. And that's what we try to normalize to get rid of that up, down pattern. This is the line that I'm going to carry over to the next chart. This is at 1 ppm. So these are very small concentrations, less than 1 ppm in rock in the bulk solar system. And that line is equivalent to this line up here. Well, it's not equivalent to this line. This is Nask. This is a shale version. So if you take the whole composition of the solar system and then limit yourself to just the sedimentary component, there is some fractionation and you get this line for Nask, which is the North American shale composite. It's a combination of 40 different shales blended together. So that's a really great way to look at rocks, is to normalize them to this line and get rid of that sawtooth pattern that way. There's also some people who study rare earth elements in the ocean, and they proposed the North Pacific deep water normalization, which is down here. It's different. It's not the same as Nask. It's 6 orders of magnitude off, which is the same as the difference between the world's tallest building and the width of a human hair. So that's a pretty big difference. Mathematically, though, you can just shift it down by 6 orders of magnitude, and mathematically, that works. You can compare, you can measure the height of the tallest building in human hairs. Nothing wrong with that. But you can see that there still is a structural difference between the oceans and sedimentary rocks. Cerium behaves differently, and also the slope of those lines is different. So what we did is we took the rare earth data that we had, and we just plotted up a proposed new normalization just to see what it looked like. And we didn't know if we were going to stick with this thing, if it was going to be any use to anyone. But we called it the Wyoming Basin Produced Waters normalization. And we got yet a third different pattern here. The heavy rare earths are good. They stick together. They're exactly the same. This means that heavy rare earth elements are reliable. They're the same in the ocean as they are in rock. They're the same in the Wyoming Basin Produced Waters as they are in those locations. We do, however, have differences. We have yet a different cerium behavior that's intermediate between oceans and sediments. And we have really weird europium behavior. We have a positive europium anomaly. We think that that's probably due to the different redox state that europium can have and the different redox state that cerium can have. Most of these rare earth elements are 3+. Cerium can sometimes be 4+, and that changes its chemical behavior. Europium can sometimes be 2+, which allows it to substitute for calcium. And then when it changes back to 3+, it has to fall out. It gets ejected from the structure. So we think that that might be what's going on here. We see weird behavior on the side of europium as well. We get gadolinium and samarium also being odd. So I'll give you a little bit of background on how we made that black line. We took our 38 samples, and like I said before, Nask used 40, and they were blended in unknown compositional ratios. Here, we're taking at least a known composition, giving each one of our 38 samples a known equal weight. So by some metrics, you could argue we're better than Nask. But Nask is established, it's been used for a long time. It's certainly the champion out there, the tried and true champion. So we took a histogram of our rare earth elements and how much their concentrations were. We fit a Gaussian to those. This is thanks to the work by one of my colleagues, Yuri Ganshin. And we then took those Gaussians, and you can see that they just line up with where this is. I didn't quite size those right. But that's where we got our normalization for the Wyoming Basin produced waters. Quick answer question I see that popped up in chat. Charles, is there potential from contamination from the separators or other equipment, dirt, sludge in the separators? Yes, I wish I had held questions until the end. That's definitely possible. In fact, that is actually one of the things I'm going to propose in one of our cases. I mentioned that there were holding tanks in one of our samples, and it is likely, in my opinion, that those tanks are the source of the weird behavior we see in those samples. So I'd buy it happening in one place, and if it can happen one place and be detected, we have to consider it in all the others too. So that is a real risk. Don't really know how to control for that, how to back it out. We took some samples later that were clean samples from the wellhead. And so those wellhead samples, which I'll actually show you here very, very late in the talk, from this red box in the Laramie Basin right outside my back door, those wellhead samples will be immune from the risk you bring up. And they might, because they are cleaner, indicate that that's what's happening. Nevertheless, we think we can get some useful data out of these samples. We think we can tease it out and see the signal behind the contamination, if that's what's going on. We don't have any proof one way or the other. So the 4 places we took water from were the Powder River Basin, the Wind River Basin, the Washakie Basin, and the Green River Basin. And like I said, we also took samples from the Laramie River Basin more recently, but that's last year's work. That's 2019 work. And I'll just show you a little bit of that at the end. The Green River Basin, it is the place where I think what your question brings up might be happening, because those samples were held in a tank for a very, very long time. And that is where, if there were contamination, it certainly had time to mess things up. The separators in the other locations, they had maybe an hour of exposure, and if we dumped them beforehand, it was relatively fresh water flowing through the tank, through the sludge and whatever else it was. But it was a much more limited exposure and probably better. So the samples that we took had a huge variety of geochemical parameters. Their redox varied from -200 to +300 millivolts. Their pH ranged from 9.5 to 6.2. Granted, that's within natural waters, a little bit alkaline there. Like I said, they were hot, and they were also pretty salty. They came from hugely variable depth, as little as 7,000 feet down, which is about where most of our oil plays start in Wyoming. And there are some that are shallower. And went as deep as 25,000 feet, which was in the Wind River Basin, and that's some of the deepest wells in Wyoming. I think they are the deepest wells, and I think they are the deepest operating wells for oil and gas exploration in the United States. It was a real treat to sample those. They were hot, thermally hot, not radioactive hot. So to go with the water samples, we took out a whole bunch of rocks out of the Core Research Center in Denver, in Colorado, and we took these samples from places that were basically the same as where we grabbed samples here. You can see that they're basically overlapping as much as we can. There are some areas that we had to go for rocks that were the right formation, but just the wrong location. And so that's why you see these other X's spread out over other places. They're a mix of core and sample and cuttings. Our geology guys, the hard rock people, really love core and really hate cuttings because you don't get any context with cuttings. Nevertheless, we sent it all out for a rare earth analysis. We did half of it in-house, well, checked our numbers. And we got back pretty boring shale behavior. So when normalized to shale, when normalized to the Nask, these are basically flat lines. There's a little bit of heavy rare earth depletion, a little bit of light rare earth enrichment maybe, but they're basically flat lines. The rocks are unremarkable. They're not going to get us a solution that tells us cool stuff. However, we did see that the Madison, which is a carbonate rock system from which we have 2 samples that are special, and I'll show you later, we found that those are very, very low, very, very low dilution, very, very dilute. They don't have very much rare earth elements in them. So carbonates don't have rare earths in them, but basically everything else we studied that could be contributing rare earths to the water is basically a flat line for Nask. So here's the data. I'm going to go through these things pretty quick, I think, get us to the results in future work and questions. So here in the Wind River Basin, basically flat line for Wyoming Basin produced water. It doesn't have structure beyond what you see in the Wyoming Basin produced water. So this is behaving like that black line that I showed you earlier, a typical behavior for Wyoming Basin produced waters, with the exception of the Co2 here, which we think has a conduit via fault that connects it to the hot water in the basement and gives it a signature more like those carbonates that I'm going to show you in a moment. I'm sorry for giving you a foretaste before we actually get to the data, but this Co2 data imitates the carbonate data that I'll show you at the end of this. Otherwise, they're unremarkable. The Powder River Basin, mostly unremarkable, but we see a unique gadolinium enrichment here. We see a peak in gadolinium. And gadolinium is found in slightly higher concentrations in the ocean. And so we think that maybe this is an ocean signature. The only problem is we're in Wyoming, a desert, landlocked, far away from the ocean. How did it get there? Well, it turns out that the time period of the shales that contributed these samples with the gadolinium enrichment in the Powder River Basin from 2 different locations in the Powder River Basin, it coincides with the Western Interior Seaway's greatest extent. And in this area, the Western Interior Seaway was present for longer than it would have been otherwise. The Powder River Basin, just for reference, is in this corner of Wyoming. And so the Western Interior Seaway, the Cannonball Sea, stuck around here for a little bit longer. Maybe that extra time gave it a chance to contribute gadolinium to the shales, which then maybe contributed it back to the water. That's our current working hypothesis. We also see 4 samples with heavy rare earth enrichment, and those are the ones that have the highest shale fraction. So there might be a correlation between shales and produced waters that have high heavy rare earth content. The Washakie Basin is, again, fairly standard. Basically a flat line, and these are noisy because we're working at the very limit of what an ICP-MS can handle even after the chromatography separation. So this extra noise, although it's unpleasant to see, you just have to sort of look through it and try to look for the bigger structure. What we can see here in the Washakie Basin is this europium anomaly, different from the gadolinium anomaly. This is europium now. And it could be that this is contributed from calcium-bearing minerals. However, the rock is very low in calcium content, so that's a little bit of a mystery. It might be pulled out of calcium-bearing minerals due to redox. This part of the basin does have rock enrichment in vanadium, and vanadium we know is a redox-sensitive element. It goes into and comes out of elements, out of minerals based on redox. It mobilizes and demobilizes. So that's the working theory, is that there's a redox signal here. Otherwise, these are all remarkably regular, and that's because they're from a single reservoir. The other ones all came from different producing intervals. This is from the Lewis Almond in the Washakie Basin, which is a combined reservoir. Water can flow from one to the other. There's no real bounding between them. And so that could explain why it's so regular. Back to the question earlier from Mark, this is the Green River Basin. And this is where we were pulling out of tanks. And so there was a lot of significant noise here. It's even a sawtooth pattern, which to me says we pulled rare earths out of solution in a way that's not based on their concentration, but made an absolute reduction in all rare earths by some fixed amount. We precipitated lutetium just as much as we precipitated lanthanum. And one way to do that is to co-precipitate with an iron-bearing phase. That's actually been proposed as a way to do an analysis. And so this might lend support to your tank idea, your tank question. That could be what's happening. These are the carbonates that I talked about earlier and that I wanted to spend a little bit of time on. These carbonates come from two different basins. I haven't shown you these lines yet. This is from the Wind River Basin in green and from the Green River Basin in blue. They're carbonates. They're both the Madison Formation, but they're basins apart. They're not connected by water. There's a mountain range between them. And yet they have very, very similar pathways until you get to the heavy rare earth elements. And we think the difference between the heavy rare earth element performance is based on how close they are to the granitic basement, which could be hydrothermally leached and contribute heavy rare earth elements. In the Wind River Basin, this carbonate is directly on top of the basement, and so it might have an easy access to that heavy rare earth enrichment. In the Green River Basin, it's got a few layers between it, and so maybe that's keeping the heavy rare earth enrichment from getting into the carbonate signature. But the carbonate signature is this guy. And we see the same thing in the CODI because there's a hypothesis that it's got a conduit via that fault that we think is transmissive into the carbonate. So it's cool because we're seeing actual structure that matches up with what should be happening. We're seeing, with confirmation bias, that carbonates are detectable by rare earth element water, aqueous rare earth elements. And those are carbonates that are unique because they have different rare earth concentration in the rock. So I'm now on results here, and I'll get through this thing, I think, in about 8 minutes. That's good. So our results. What did we come back and tell DOE? Thank you for your support. We've gone out into the field with the blindingly blue sky and the desert below. We had a great deal of fun collecting samples, doing cool work. Some of us doing work inside a clean lab, and others of us getting to work in a normal lab and enjoying ourselves. Thank you. Here's what we found out. And so these are the results we told Department of Energy. Rare earth elements can sometimes occur in groundwater in excess of 1,000 times their seawater concentrations. Now that's average seawater, admittedly, and on average, the basin produced waters we found were lower. But if you go to the right spot, you can get rare earth element concentrations way, way, way above what you get in the seawater. And here I'm showing some samples that I didn't talk about from our collaborators at USGS. They contributed some samples from the Appalachian area. And here you can see that we have huge amounts of cerium. This is now back to seawater normalization, by the way. We have about 2,000 times as much cerium in one of these samples, and also a whole bunch of europium in these samples, more than there is in the seawater. You have about 1,000 times more than you have in the seawater. Those are two interesting elements. Cerium, there's a plethora of cerium out there. It's all over the market. It's not economically valuable. It's called an excess rare earth element. But europium is a valuable rare earth element. And as long as that market stayed where it is, and I can talk more about markets later, during questions, this could be a blessing. This probably is a curse because it's rare earth elements that's going to go in the same places, do the same things, but is not really all that valuable. This could be a blessing. It could be a curse. Who knows? Regardless, we can show that there's site-specific markets here. There are some places that are good for heavies, some places that are good for europium, some, if you wanted it, that are good for cerium. And this is the statistical output from our collaborators at the USGS. This is what their computer model did when it churned through all that nasty looking data I showed you at the very beginning. They output a prediction for all of the continental US based on the produced waters database that they hold. And you can see that you guys down in Texas, you guys have some of these highest predicted potential areas. And we don't know that those are good, and this is not an endorsement to go out there and buy land and make money on speculation. This is merely saying that the model predicts that there are good spots there, and further work should be targeted at those areas to say, yes, there is actually something here, or no, sorry, the model was wrong. You need to train it better. This was using machine learning. It was called an ESOM, an Emergent Self-Organizing Map, for those of you. I know Sahar does a bit of that machine learning stuff. And we out here in Wyoming sort of lucked out. They told us the truth, and we're grateful for that, but we don't have any of those red triangles that you guys have. Oklahoma gets a few, and some other places get some, Louisiana. So a lot of these are very low concentrations, parts per trillion, but they are there in all continental groundwaters, and they are measurable via INL's method, Idaho National Laboratory's method. This means that if the economics were extreme, like really extreme, anyone could supply rare earth elements. There is some there to use. Whether you'd want to is a matter of just how extreme those economics are. We also found that aqueous rare earth element behavior imitates what was already known for rock rare earth element behavior. This is a principal component analysis, again from the USGS, and we can see that all the heavy rare earth elements have similar vectors, which is what they should have based on rock, and all of the light rare earth elements have similar vectors. We also see that among the light rare earth elements, the distinction that some people draw between light rare earth elements and medium, middle light rare earth elements here, that also holds. And we see that scandium actually falls among the middle rare earth elements. So that sounds like a bit of confirmation of what we already knew. It's good to see the water match up with the rock. I see another question, and I think I will answer it in a few slides. This is good. This means that principles for how they work in rock should work for water. And it's important to remember that gadolinium is over here in the lights due to the way that orbitals fill and how at this particular configuration, total pairing energy is about the same as the orbital energy. And so that means that gadolinium really should be over here. It should be one of the lights, not one of the heavies, as we would naturally assume just by doing the counting method that we'd all get in Chem 2. This is more of the statistical output from USGS. You can see that they did the heavy lifting on the results. They looked at a whole bunch of different variables, and here we have, and they tried to make a map. And so what you do to read these maps is you look at them and you say, which of these maps look like other maps? And if they look like other maps, it means that what they were mapping co-varies, and then you've got a relationship between them. Here you got praseodymium, and here you've got ytterbium. And you can see that their maps are kind of the same. You've got a map with a highland here, a white chunk, and a little bit of extra land extending down. It wraps around top to bottom, left to right. It's Pac-Man space. And you've got a little bit of land up here. So the rare earth elements co-vary. Lights and heavies, they go together. We knew that. Europium is kind of like them. It's got the same island here. It does a little bit of the same wrapping around to the top, but it also has unique land structure over here, meaning that europium sometimes behaves differently than the other rare earth elements. Chlorine, which has often been proposed, doesn't match up. Fluorine, also proposed often, doesn't match up. Hydrogen, pH, or temperature, or silicon, all the same story. Here, though, you can see that silicon and fluorine sort of match up in waters. We knew that. So this is really challenging because we don't know what it is that's causing these things, and that's an area of future work. This is the most recent work that we collected directly from the wellhead. This is the stuff that we know was not contaminated by a separator in response to that earlier question. And here we can see very nice, clean lines for the heavies. It's kind of refreshing to see that the basin, the Wyoming Basin Produced Waters normalization is working. Over here we've got Nask, which produces similarly clean lines, but at a very different order of magnitude. And we can also see the unique europium behavior in both of these, although they're lacking a samarium enrichment and gadolinium enrichment that we've found in other waters. So if you were going to say something about what might be contaminated as a result of exposure to separators, it could be this gadolinium thing, or it could be that Western Interior Seaway hypothesis we proposed. It could also be that the exposure to the separator does something to samarium or makes some of this movement with the light rare earth elements, because you can see it goes from flat when normalized to Nask to wavy when it's normalized to the other produced water samples. You can see the difference between those. So future work, I've only got 3 slides here, and then I'm going to take questions and maybe talk about some coal ash work that's really exciting for the future. We saw from the USGS's output, their statistical model, that there's some unknown variable out there, and we have no idea what it is. We know that there's covariation basin by basin. There are trends, and we know that there's something that is varying with those basins and making this rare earth expression, but we don't know what that is, so we need to go look for it. We've got a whole bunch of theory about what it might be. Future work, we don't like to get a bigger sample set. The more samples we get, the more we'll tease out variables like separator contamination, if that's what's happening. And the more we'll be able to get real anomaly detection. Maybe we'll get a breakthrough on what that unknown variable is with some extra work. As you saw, thanks to that high amount of potential in Texas, it would be great to work with you guys. Shameless pitch there. Texas has a great potential. We could look at Oklahoma, northern Louisiana, the Colorado-Utah border. It'd be great to figure out those things and do more work with someone. We've also moved on to looking at used water, cooling water, water from the Solvay process for soda ash production. Coal power plant ash ponds also are very interesting. Here's a coal water ash pond. This is now a linear normalization, and it's based on Nask. You can see that we really break through in some parts of the ash pond on heavy rare earth elements. And these are not the trivial amounts that they were in waters. These are still parts per trillion, but they're many more parts per trillion. So ash has potential. We'd like to figure out that. Future work, which we actually got to realize, was to do something that can help Hari not live inside a clean room inside a clean room. The guy is happy doing there. He deserves kudos and all that. But this column chemistry is, it could be a source of error. We don't think it is. They've done a whole bunch of blanking work, and we're sure that it's safe. But nevertheless, it'd be nice to remove that step and have a direct analysis where we just pull the sample from the field and throw it into a measurement of some sort, like this elegant triple quadrupole. Well, they actually got that, and we were able to run one sample, our sample number 64, through their lab and also 2 other labs doing other methods. And the agreement isn't perfect. That's the way it will always be when you send the same sample to 3 different labs, but we got pretty close. So we're pretty glad about that. This improvement did actually get realized, and it did help. So that was a success story. Here's what I showed you normalized to Nask earlier. You can see Wyoming, we've got some places with heavies, and we've got europium enrichment. The USGS guys had this, and the scale is the same. They had a whole bunch of europium, and they actually had enrichment in lights and heavies that we didn't have. To learn more about it, you can talk to Mark Engel and read some of these papers. Everything we publish is on the GDR. I recommend reading the final report, which is this submission number available at this web address. You can grab it out of the recording. And I'd like to acknowledge our team members who helped us out with doing this work and show you some references, again, which you can pull off of the recording. This is the coal ash sampling. This is me reaching into a coal ash water pit coming out. This is future work. This is me grabbing from a different power station. And we did some preliminary analysis that shows that this pattern matches carbonates, which makes sense because scrubbers add lime, and they also have heavy rare earth enrichment. So this would be cool. We'd love to do more work in this area. And with that, I'm going to stop, take questions.
Thank you very much, Charles, for your interesting talk. And it is very interesting to hear that Texas has a high potential for REE, and it brings the opportunity for our researchers for collaboration with your group. So I think there is one more question by JP Nicot in the chat room.
Oh, oh yes, that's the $1 million question right there. Yeah, let me see here. So timing is really important when you talk about economics. This is a publication by Fernandez. It's in my reference list. But she goes through a whole bunch of, or he goes through, I don't know, they go through a whole bunch of different pricing history. And so the price changes year to year. You can see that if in 2000 someone put all their money on samarium, they would have been very happy for the next 6 years, and then they would have been very disappointed. So I, as a geologist, can't really tell you how high they need to be economic. I can tell you the Mountain Pass mine is working at multiple parts per million, but those are in rock, and rock has to be ground up and then leached and separated and a whole bunch of complicated stuff. In water, we get a gimme. We just pull it out of the water directly. And so that's sort of the hope here, is that although our concentrations are much lower, maybe the extraction is so much easier, it's worth it. Also, I see the other question earlier, and I meant to address that here. The USGS found huge European concentrations in the Marcellus, Golden, and Brea, but only in some places. Other samples from those same formations were very low. So that should answer your geologic formation question, I think.
I'd like to follow up on my question that I had earlier and on the sludge issue. So the sludge is obviously precipitate from the water that's being produced. So it does come from the formation. And the way I would say it's not only the contamination of your samples with the sludge, but it's obviously that your water composition is already affected by the precipitation of the sludge in the stock tank, right?
Yeah.
So I think I would actually disagree with you that the degassing in the well bore is the issue of concern, because that would be sampled in the water that comes out of the wellhead. It's the degassing in the stock tank that I'm concerned about. So I think sampling from the stock tank is problematic in some ways, as you have seen. So I know it's hard in many cases to get access to the wellhead and do the sampling there, but
Yeah.
I think it's important to have good data to begin with. And my recommendation would be to perhaps at least treat with caution the samples that come out of the stock tank.
I couldn't agree more. The stock tank, even if the outgassing is a problem, the stock tank is yet another problem, and it's certainly not going to help. So we should try to avoid it if we can. We got stuck with the only thing we could get in the Green River Basin was the stock tank, so we had to take that. But we saw confirmation for what you're proposing, and those samples were noisier. The separators, which are different from a stock tank, the fluid goes into the separator first, splits into its 3 phases, and then one of those phases is put into each of the stock tanks. In the separators, we have the ability to dump them. And so the water will flow through from one side, turbulently separate, and then laminarly separate later. And there will be sludge in the bottom of the stock tank, but because it's always moving, and because we're able to flush it and then take our sample, the separators are better. The stock tanks are full 9 yards, exactly what you just described. The separators are more acceptable, and the wellhead, of course, is ideal. I think that the CO2 outgassing is important because it changes pH, but I think you're also right that the sludge contact and precipitation is yet one more thing that could go wrong. So I'd say both and. Yeah. I see one more question popped up in chat. Mark, are there any proxies, elements associated with REEs that could be more easily measured? We had the exact same question. Yeah, it would be so much easier to just measure by proxy. We don't see any directly. Yttrium is the go-to because it's a rare earth element. It moves the same way, but it's present at much higher concentrations than the rest of the rare earth elements. And actually, to boost the numbers, that's part of my cynical reason. I think cynically that some people add yttrium just to boost their rare earth numbers, make it look more economic than it really is. But that's me being cynical. The yttrium would probably be your go-to, and it's not that much easier. It's still hard. Because of that work that I showed that didn't have any of those things matching up, we're sort of in trouble. There's no USGS found parallel. So not yet, but we want one. Any other questions? Verbally or by chat.
Yeah, please unmute yourself if you have any question for Charles. So Charles, I have a question. How do you see the future of REEs in terms of commercialization?
I can cheat actually on that one. I actually think that this this idea of the fly ash from coal-fired power plants, as crazy as it might seem, actually is the saving grace. I think that the water is very dilute, but it does have the heavies that we care about, and it might be moving the heavies from one part of the ash pit to another, which would then boost the concentration further. I think the future of rare earth element mining in the United States is not going to be a return to Mountain Pass, although that's certainly part of the solution. They've got an awful lot of light rare earth elements, which tend to be less valuable. I think the future of it is going to be mining these coal ash pits, which have been built up over 50, 100 years. And they contain a tremendous volume of ash. That ash has been leached with rainwater coming in from the top in a process that's basically a natural analog of a heap leach, which is an accepted way of doing extraction by humans. So I think that mining ash pits and selectively mining coal seams that have rare earth elements in them, and I'd recommend people to Davin Bagdonis's work. He had a Pittsburgh Coal Conference paper that showed that the parts of the coal seam out west that you don't mine and that have been underrepresented and under measured, the parts that you don't mine actually are the parts that have the highest rare earth element concentration. And so if we could build or convert one of these power plants, which are closing right, left, and center, and if we could convert one of these maybe to burn high ash content coal, the stuff that people thought was worthless and had to be thrown away, we might find that we can produce an ash that is very valuable and very concentrated. He's getting numbers at like 1,000 ppm once you ash it, which is pretty good. And this ash is already disaggregated. So instead of hard rock mining, we have to grind stuff up. Here, you just throw the acid or the water or whatever you're doing for your extraction right onto the powder. So I think that's where it's going. And I think water is going to play a part in identifying the part of the landfill that is enriched. It might be the bottom, it might be halfway down, who knows?
Yeah, I think there's one other question by Tanquay.
Oh, yeah.
Yeah.
RE concentration is about 1,000 times higher. Where's the origin and what are the carrier minerals? Yeah, I've cunningly stayed away from carrier minerals. We don't really know in water how these complex and how they move. The paper by, they've published a lot of papers, Mikoslav and William Jones, they propose that chloride is the main way that these things complex and move with water. That's counterintuitive. People thought it should be fluoride, but there's just so much more chloride in water than there is fluoride in the water that they think that that's actually more important for mobilizing rare earth elements in water. So that's the guess for how they're moving as a species in water. Carrier minerals in the rock, I've cunningly stayed away from that because it's actually the specialty of people like Davin, who I've mentioned earlier, and he'd be better placed to tell you about that.
Is there any other question? Okay. So thank you again, Charles, for your interesting talk, and thanks everyone for your attendance and for your great questions.
Thank you.
Hope to see you. Yeah, hope to see you next week at 9 a.m. Thank you, and have a wonderful weekend.
Okay. Shoot me an email if you have other questions.
Thank you.